All right. What's that? Yeah. All right, let's go ahead and wrap up 11.6. We've got a couple more examples to do in 11.6, and then hopefully you can hammer out all the homework. And then we'll do 11.7, 11.8. We got a lot of math to do. Come to the right place if you want to do math today. Yeah, we've got a lot to cover today. All right, so let's compute some indefinite integrals. And the indefinite integral here is done by integrating term by term. And nothing too complex at this moment. We're just using the power rule for the first few of these. The last one is kind of a disguised power rule that, well, maybe I shouldn't even call it power rule because it's slightly different. So let's integrate. So we are going to integrate little r with respect to t to get the indefinite integral. So the first component, we'll do it, and we will get, we add 1 to the exponent, get -3, divide by the new exponent. So we get -5/3 t to the -3 minus t cubed over 3. And then the second component, we'll get t to the 7/7 minus t to the 4th. And the last component, integral of 1/t, gives us what?
Is it natural log of t?
Yep, exactly what you guys are thinking. Natural log absolute t. Exactly what you're thinking. Natural log of absolute value of t. And then we have to put in an integration constant, so we can either just add it as a vector constant, so that implies that we have a numerical constant for each of the 3 components. So you could put a little plus C1 plus C2 plus C3 inside each component, or you could just do it like that. Either way. So that'll be our indefinite integral. It's a collection of all antiderivatives. Next one, same idea. We're going to find the indefinite integral. So we're going to integrate term by term. And here we have a complicated first term, integrating 2 to the t. How do we integrate an exponential?
Natural log of the base times the base to power. So natural log.
Natural log of 2 times 2 to the t?
Yeah, which.
So if you can't remember, you have to do some sort of base adjustment. If you don't have an e, you're going to have to divide or multiply by natural log of the base. And if you're not 100% sure, you can figure it out by then taking the derivative of this. You know, there's a few ways you can test. Let's go back to, let's see, do I have space down here? Let's go down here for a second and just suppose that we have y equals 2 to the t. There's a couple of ways we could rewrite that if we can't remember how to take the derivative of it. We could try to rewrite it in a way that involves exponentials or logs, something that we know. Anyone have an idea of what we could do here?
T to the y equals 2?
You could, let's see,
Is that
t,
right?
not I don't think that's true, that t to the y equals t. But you have the right idea. If you took the natural log of both sides, if you take the natural log of both sides, you'd end up with this, correct? And then you could use implicit differentiation. Now this ln2 is just a constant. So we could differentiate both sides with respect to t. So this, you learn in Calc 1, this whole implicit differentiation thing. So we are going to take the derivative of both sides with respect to t. And when you haven't dealt with logs other than base e or exponentials other than base e for a while, it's not a bad idea just to go through, just start from the beginning. You know, try to figure out a way to determine whether you divide or multiply by that ln2. So here, derivative of a log, 1 over the inside times the derivative of the inside, which is dy dt, or we often just call that y prime. On the other side, what's the derivative? Natural log of 2, right? That's a constant times t. Derivative of a constant times t is that constant. We multiply both sides by the function y. So we we end up with ln2 multiplied by y. So we do a back sub, y was 2 to the t. So what we see when we differentiate is that we multiply by natural log of 2. So what do you think we do if we integrate? Divide by natural log of 2. So up here, divide instead of multiply because we're integrating. So we will rewrite that as 2 to the t over natural log of 2. And that's kind of a common pattern that we see with the reverse chain rule thing. We divide by the derivative of the inside. So there's always, or at least there's frequently, a division instead of a multiplication when you're integrating. So you could use that general principle to remember. Any questions on how we came up with this idea here? Implicit differentiation, is that familiar enough? Yeah?
Will you remind me why you put the dy dt into the, yeah, that guy.
So this is chain rule. We're differentiating with respect to t, but that's not a t. That's a y. So we're assuming that y is a function of t. We're assuming that there is an independent variable of t that's hidden inside the y. So then we have to chain rule it. We have to do the derivative of this with respect to t as the chain rule piece. It's 1 over the inside, and then if the inside can be differentiated, we have to differentiate it with respect to the variable that we're using as our independent variable, our assumed independent variable.
We usually write that as y prime though. Right?
Yep, you can write that as y prime, absolutely.
Okay.
The only reason sometimes with implicit diff, we sometimes don't write the y prime just because then it's not totally clear, unless you put y prime of t, that the independent variable is t. So a lot of times with implicit differentiation, they'll do it this way just to emphasize that the independent variable is t. And we'll do more of that. We'll do some more implicit differentiation later, of course. All right, so that's our first term. And then we integrate the second term. And the second term is going to be, what's that going to be?
You're going to start with natural log of the absolute value of 1 plus 2t, and then will you multiply that by the derivative of 1 plus 2t?
Okay, so great question. So certainly we see that piece of it. We have to, again, we're dealing with, do we do a division or multiplication, what happens? And I like to call the form of this integrand a log form. And so one of the basic properties of a log is that the derivative of the numerator, the derivative of the denominator is in the numerator. So if you have something like this, if you're integrating a function and its derivative is in the numerator, that will integrate to natural log of the absolute value of the denominator. So that's what log form is. It's in log form if the denominator's derivative is in the numerator. That's almost in log form. We can just do a little tiny finagling. So if we're trying to integrate 1 over 1 plus 2t dt, what's the derivative of the denominator? 2. So let's put it in the numerator. But if we put a 2 in the numerator, we have to put a 1/2 out in front to offset that 2. Now it's in perfect log form. This will be 1/2 natural log absolute denominator. Right? So once we have it in perfect log form, we know how to integrate it. So if we do that little multiplication trick, we see that the 1/2 is going to pop out in front right there. And then we have to integrate natural log of t. Wow, we're really blowing out cobwebs. How do we integrate natural log of t?
You don't by parts?
I do.
Isn't it 1 over?
Maybe you don't. I integrate natural log of t all the time.
Or is it x ln x minus x plus c or something like that?
Yeah. Right, so what was the technique?
Integration by parts?
Yeah, integration by parts. Right, isn't that what it's called?
Ultraviolet voodoo.
Ultraviolet voodoo, UV minus integral of v du. Right, ultraviolet voodoo, integration by parts. So if let's go back for a second. Let's suppose we have y equals natural log of t. And actually, I don't want to write it that way. I just want an integral here. And let's make it an x just to go back to where we would have done this in Calc 2. So you can integrate that directly. You know how to differentiate it, but you don't know how to integrate it. The derivative of it is 1 over x, but the integral of natural log x, well, we have to use integration by parts. So we have to parse this into a dv and a u. You can't put the natural log of x with the dv because then you have to integrate to get v, and you don't know how to integrate it, so it has to go with the u. So we do this, natural log of x, dv is going to be dx. You differentiate over here so that you get du equals 1 over x dx. And you integrate over here to get v equals x. You choose your constant of integration to be 0. And then you end up with uv, which is x ln x, uv minus the integral of v du. And what is v times du? X over x is 1. So the integral of that is just going to be x. And then we add a constant of integration.
You mean t?
Oh, I should put t's in there. Thank you. Yes. Yes, we need to go back to t when we're up here. T ln t minus t. And of course, you can double check by taking the derivative of t ln t minus t, and you'll see that, oh, wow, we get ln t. It will work. All right, so yeah, a little exponential with a non-e base and a little integration by parts. A little voodoo. Definite integrals. Piece of cake. If you can find the indefinite integral, the definite integral is simple enough. We just plug in the upper limit, plug in the lower limit, take the difference, and we're done. We'll go through this pretty quickly. So we integrate each of these terms, or components more correctly. These are components. Components are parts of a vector. Coordinates are parts of a point. So we integrate from 1 to 4. And then we plug in the 4, plug in the 1, and subtract the 2, and we're done.
Do we have to do it separate for each function? Like,
Say that again?
do we need to evaluate from 1 to 4 for like?
Oh, we can do
this
it all at
and
once.
that and that?
Yeah, we could do it. We can do it all at once. So we can say, let's do it all at once. So for each one, we're going to get a vector. We'll get a constant vector. So when we plug in 4, we're going to get 128, comma, is that 512? Comma, 4 times 4 times 64 times 3, 180, 192, perhaps. And then plug in the 1, so 2, 2, 3, and then we subtract them. As long as I did the arithmetic right, we would end up with that constant vector. So just like a definite integral of a function, you end up with a number. Definite integral of a vector function, you end up with a constant vector. So we end up with a constant vector for a definite integral. No variables. Variables were dummy. Variable is just there temporarily. Cool. Little trig. Little trig. Again, I'll always do these with components, but if you want to keep the I, the J, and the K, and just be really careful, use magic markers for the unit vectors. Do something to make sure you don't goof it up. Integral of secant squared. Tangent. Tangent of t. And then integral of cosine. The sine, that doesn't change. The sine, we leave it as a negative. And then integral of -1 is just negative t. Whoops. That's not the evaluation symbol we use. We go 0 to pi over 4. Plugging in pi over 4, tangent of pi over 4. 1. So we're at 45 degrees, pi over 4. And the slope of that line is 1. Plugging in pi over 4 there. Sine of pi over 4 is root 2 over 2. So we have minus root 2. Plug in pi over 4 there. And you absolutely could do what Samantha suggested and do tangent of pi over 4 minus tangent of 0. Minus sine of pi over 4 minus 2 sine of 0. You could do it all in one piece also. Totally works. And then tangent of 0. Nope. Tangent of 0, 0.
What am I thinking?
So you can think in 2 different ways. So if you're trying to think about the tangent of 0, you're thinking about your unit circle and you're at 0 degrees or 0 radians, you're over here. Tangent is y over x. Geometrically, you're thinking it's the slope of the terminal ray here, or you're thinking, okay, what's the graph of it look like in the xy plane? And tangent goes right through the origin, so tangent of 0 is 0.
What is it approaching?
This is is that what you're asking?
Yeah.
So that's a vertical asymptote at pi over 2 and minus pi over 2.
That's what.
And then, let's see, plugging in pi over 4 for sine, plugging in 0 here. Sine of 0 is 0, so we get 0, 0. So that part doesn't contribute much. So we get a definite integral that is equal to the constant vector right there. Yeah. We still have donuts and cookies up here for anyone. I know there's some people that walked in that look hungry.
Wait, what?
I'll take the donut.
Grant, I've never seen you turn down a donut.
Well, I've never been offered a donut in your presence,
That's
as
true.
far as I know.
Exactly. That's true. And then there's cookies. Any cookies in here? Seems so unusual.
Wants the donuts.
All right, so that is the last of the exercises from 11.6. So let's go over to 11.7 and start doing crazy applications. Some cool Calc 3 stuff. This is the beginning of some really practical types of problems. We're going to talk about projectile motion. Physics. Reality. Projectile motions. We're very familiar with projectiles.
That's what I always think of.
Where is projectiles. Some projectiles are better analyzed than others. All right, so what we see here is a curve in 3-dimensional space. And that curve in 3-dimensional space has a velocity vector attached to it in different places. And that velocity vector is indicating the direction of the motion. And so that is also referred to as the orientation of the curve. Now, graphing a curve in 3-dimensional space is really hard. There's a cool program that I've mentioned to you, GeoGebra. You can at least get a sense of a lot of these. I might as well just bring it up because we will see a few curves today that we might want to just get a sense of what they actually look like in 3-dimensional space. So if you go to geogebra.org, combination of geometry and algebra, and you click on 3D graphing down here, right down there, 3D graphing, we can graph in 3D here. So if we wanted to graph just a surface, you would just kind of type it in. But we're graphing curves, so we're dealing with parametrizations. So we've got to enter it a little differently. Capital C-U-R-V is how we enter curve, and then parentheses. And let's just suppose my curve was cosine of t. You have to put parentheses around that t. You can't just write C-O-S-T. It has to be of t. I'll do a helix or something like that. So those are the 3 components. The x component is cosine, the y component sine, the z component's t. And then we have to tell it what the parameter is. So the next spot's going to look a lot like the third spot just because they're equal. And then we give it a range, 0 to, say, 2 pi. And then it will show the graph over here. So it graphed it just from 0 to 2 pi. Obviously, we could make that go 0 to 4 pi. There's lots of different things we could do here. And you can label your axes. I don't see the axes labeled here. If we come over to settings, pang, and we wanted labels on our axes, you can just click if you needed them, you can put them, go for each one. We don't really care right this minute. So you can kind of, like I had mentioned before when we talked about a helix, if you were to look straight down the axis that it's kind of curling around, it looks like a circle if you project down onto the correct plane. But this program gives you a pretty cool idea of what some of these curves look like. So we can fiddle with these components over here. Maybe this is 2 sine of t. Whoops, 2 sine of t. Should change it. That looks more like a tilted ellipse.
How do they make their money?
GeoGebra was developed by a couple of guys, a couple of math professors who got an NSF grant. So this was funded by federal government money that now it's all open source. And they update it every year. It gets better and better. So yeah, it's pretty nice. Pretty nice program.
That our school used offline app a few years back, and it was just half the buttons caused it to crash.
Which program?
GeoGebra.
Oh, really?
Yeah.
Oh, in the 3D grapher?
Well, actually, no, the 2D grapher.
Yeah, 2D grapher shouldn't crash much. I've used it for a while. It should be pretty stable.
All right. Yeah. I guess it's improved in.
Yeah, it's definitely gets better and better every year. Okay, so that's one great way if you're trying to figure out what the heck the curve looks like that you're dealing with. There you go.
I think I also tried the GeoGebra app on my Fire, and I wasn't all that impressed.
So let's see. So we are up here. So that's the idea then, is we have a r is our position vector. It's locating the position along a curve. And then if we take the derivative, we're going to get the velocity. And that velocity is going to correspond geometrically to a velocity vector. And then if you take the magnitude of that velocity vector, that's going to correspond to the speed at that moment. So the longer the velocity vector is, the faster it's going. And one thing we're going to look at in the next section is something called an arc length parametrization. And the reason we may want an arc length parametrization, when we're looking at the bending that a curve is doing as the points are plotted, we were going to talk about a concept called curvature, and the faster it turns, the higher the curvature value is. And we're going to need a way to measure that degree at which a curve is bending. And the way that that's all going to be defined is by creating a parametrization for the curve where the velocity vector is always 1 unit long. So we'll get to that. But the idea is that if we have a curve in space and if the velocity vector is always 1 unit long, that means the only thing that's really variable is the degree at which it's turning. So you kind of take away the fact that it might have variable speed. If you can somehow force it to have unit speed, then you can analyze, you can do some geometry, and you can analyze the angle at which it's, or the degree to which it's turning. All right, so curvature, we'll get there next section. All right, so our position vectors, we're imagining them emanating from the origin. And at the end of each vector, we get a dot, which is representing a point on the curve. And that's what we have. And if we want to know the speed, we take the derivative and then find the length of the derivative vector. So that's what this represents. That represents speed. Speed is the length of velocity. The magnitude of velocity is speed. So that is speed. And the only difference in three-dimensional space, you have 3 components, you have 3 derivatives, you square them all and add them up and take the square root, and not too complicated. Okay, so let's talk a little here about the green vectors. So we all know that if we start with position and we take derivative, we get velocity, and if you take a second derivative, you get acceleration. And so that's the sequencing. We start with r, take its derivative, get v, take its derivative, and get acceleration. Now, when you're dealing with a curve, you have I guess there's 3 possible situations. Your particle that's moving through space could be accelerating, it could be moving at a constant speed, or it could be decelerating. Right? Those are the 3 scenarios that we're going to imagine. And the The way that we can tell by looking at the graph whether it's accelerating, decelerating, or constant is to look at that acceleration vector. So when the acceleration vector is pointing in the same relative direction as the velocity, then the acceleration or the acceleration vector is indicating that we are in fact accelerating because it's increasing the velocity. If the acceleration vector were pointing in essentially the opposite direction of the velocity, that acceleration vector would be indicating that we're dragging on the acceleration, slowing the motion down, slowing the speed down. And if the acceleration vector is 0, there's no acceleration, so we have constant speed. Right? So if you have a constant velocity, the derivative of a constant is 0. So you'd have a 0 for the acceleration vector. So in this case, we see that we are accelerating right here. And in this case here, it's going to turn out when those two are perpendicular, what do we call that in physics when the acceleration is perpendicular to the velocity? It's like centripetal acceleration. There's some centripetal force. There's some physics stuff going on when they're perpendicular. But regardless, you'll be able to, the acceleration vector is always going to be pointing, if it's not 0, is always going to be pointing to the inside of the curve. Right? It's never going to be pointing to the outside. So whatever way the curve is bending, the acceleration vector has to somehow be on the inside there. So we can't have an acceleration vector out there. It's got to be on the concave side of the curve. All right. So, and typically if you did imagine circular motion, then the velocity and acceleration will always be perpendicular. This is not circular motion, but you could have moments where the acceleration is perpendicular. Yeah.
Yeah, just a kind of something I found about acceleration, that they apparently have names for derivatives beyond acceleration. So derivative of acceleration.
Don't say it!
Don't say it.
What?
Did you skip?
Derivative of acceleration is the jerk.
And then afterwards, derivative of jerk is the snap. Derivative of the snap is the crackle. And derivative
No!
He went to the
No!
next one.
Yes.
No way!
Yes.
Snap, crackle, pop?
Yes.
After
He's
that,
right.
they have lock drop.
Yeah, I remember
And then
that.
what?
Lock drop after that.
I don't believe
And then they
this.
stopped naming it.
What?
Yeah.
I had no idea.
You fell for it.
I need to take a physics class.
Yeah, I think
Snap, crackle, pop?
I think an alternate name for the snap is the jounce on the pencil, like about the jounce.
Is this like cartoon physics?
No.
No, it's real physics.
Yeah.
These guys, whoever named them, had a sense of humor.
Yeah, I
Come
guess
on.
so.
Yeah.
It's pretty funny.
I didn't say they could do it.
Gosh. Okay, so let's go ahead and just calculate here the velocity and acceleration vectors for this given position vector. We take the derivative, and we're going to get 5t and then 12t. And the domain is t greater than or equal to 0. And I don't think I wrote down the instructions here. Oh, right here. So, okay, so it's just asking us to find the velocity and acceleration. And so we see here that we have constant acceleration. Constant acceleration.
If you have constants in both, that's how you know.
Yes, exactly. So this does not depend on t, right? That's constant. Doesn't matter. So if you drew your curve, then the acceleration vector would be the same vector everywhere. So we have constant acceleration. There's no variable in there. So it's not changing as t moves from 0 to infinity. The acceleration is always constant. It's 5, 12. And you can see here that as you're plugging bigger and bigger t's in, you can imagine the speed is getting bigger and bigger, right? Because the speed here, if we were to find the speed, we would take the magnitude of the velocity vector. So we would have 25t squared plus 144t squared. So it's going to be 169t squared, which is going to be 13t. And we're allowed to take the square root of that because t is always going to be non-negative. So we can take the square root of t squared and get t. And so we see that the velocity is just getting bigger and bigger and bigger as t gets larger. So, but there's constant acceleration. So that's the speed, that's the velocity, that's the acceleration. And if we wanted to, we could graph that curve in two-dimensional space. It'd be kind of hard to do by hand. It's not an easy one to do by. Well, maybe. You know, actually, we could graph that by hand. Should we try to do it by hand? Yeah. The enthusiasm is noted. I have to make an exam question to make up for that enthusiasm.
Okay.
What?
Yay. Graphic.
Graph it. I want to see it. I can't wait to see it. How do you do it? Okay, so if you're graphing, so some of you have seen parametric curves before, and the issue is that you know Cartesian equations pretty well. You see a y equals x squared thing, you know it's a parabola, you know what circles and ellipses and hyperbolas look like. But with parametric curves, you don't recognize them typically. Typically, you might have an instinct, but you're not 100% sure unless you eliminate the parameter and you turn it into a Cartesian equation. So that's typically what we would like to do if possible, turn it into a Cartesian equation. So this top thing here, if we subtract 3 from both sides and then multiply both sides by 2/5, we would isolate t squared. Subtract 3, multiply by 2/5. That can then be substituted into the second equation for t squared here. So we would have y equals 6 times this quantity, 2/5, x minus 3. And
Plus
what?
10.
Plus 10, thank you. And that plus 10 is on the outside, right? Okay, thanks. So what we see then is the Cartesian equation, and it's actually not too bad, right? We get 12 over 5 times x. We have some constants that we could combine. That's minus, let's see, that's 12 over 5 times that. So it's at 36 over 5. And then right, that is 50 over 5. So this tells us that our Cartesian equation is in fact a line.
Plus.
Did I add right? Somebody
Plus
check.
It
function
should be
over 5.
positive.
That should be positive. Yes, thank you. The line then it's just a line. Now, one thing that you have to remember with parametric curves is that your parametric curve, one more slide, your parametric curve is going to be a subset of the corresponding Cartesian curve because you have a domain that is restricted. So up on top, we said that t is greater than or equal to 0. So then we would have to go in and figure out, okay, well, what part of this line, if the question said graph this parametric curve, we would then have to go in and analyze. It's not necessarily, it might be, but it's not necessarily the entire Cartesian curve. Like you think about the parameterization for a unit circle, cosine t comma sine t. If you say t goes from 0 to pi over 2, you're just going to get a quarter of that circle. So you just have to sort of figure out, based on the values of the parameter, which part of the curve you get. But that's not really concerning us right this moment. Okay, let's take a look at another one. So the position vector is given to us, the position function. And when we say function in this context, we mean vector function, vector valued function. And we take the derivative of this vector valued function, and we get that. We find the acceleration of this vector valued function by doing what you think. You can keep on differentiating if you're interested in jerk and snap and crackle and pop. You can do that. We can find the speed of this parameterization by taking the square root of the sum of the squares. So 9 sine squared of t plus 16 cosine squared of t. Huh, that's a little squirrely over there. So we can't simplify that, so that's our speed. It's a variable speed depending on t.
So that means it's not constant acceleration.
That's right. Exactly. That velocity is not constant. The acceleration is not constant. Right.
So earlier you had talked about if they pointed in the same direction, it was either speeding up, slowing down, or doing nothing at all.
Yeah.
So in order to find if they were pointing in the same direction, would you just use dot or cross product on your vector?
So dot product is a great way to do it because the dot product is going to be negative if the angles form, if the vectors are obtusely related, and the dot product is going to be positive if they're acutely related, and 0 if they're perpendicular. So yeah, that's a great question. So if we took and dotted these two together, which we can do very easily, so if we did v dot a, we would get 3 times 3 is 9, sine, cosine. And just to be clear, the this is a function here because it depends on where we are on the curve. So we would have to look. We could see, if we plug in pi over 4, we could say, oh, at pi over 4, the acceleration and the velocity have an acute angle. So there we have an accelerating position. So the point is accelerating. And likewise, if we picked another point, it was negative, it would be decelerating there. What do we get? 7? Minus 7? Sine t cosine t. So this we could use to figure out if we're in that situation. Yeah. Acceleration, variable, velocity, speed, everything's variable here. All right, let's do one more of these. So, and before we go on, what is this curve? You guys should know that. That's an ellipse. So it would be an ellipse where, if you let this be x, that be y, you could solve and you would get the standard equation for an ellipse. You kind of should know that this would give you if the coefficients in front are the same, you're going to get a circle of radius 5, right, centered at the origin. Okay, so this one is sort of one of those physics application types where we're going to see that, okay, well, if the path of the particle is along a circle, then the acceleration vectors are all going to point towards the origin, and the velocity vectors are all going to be sort of perpendicular to the acceleration. We'll go through it. So the velocity is going to be minus 5 sine t, comma 5 cosine t. And we see that we end up with a constant velocity, a constant speed, I should say. Constant speed. The velocity is variable, right? If I plug in different t's, I get different v's. So the velocity is not constant. But the speed is constant. When we take the sum of the squares here, when we find the length of that vector, we get 25 sine squared plus 25 cosine squared. I'll just abbreviate sine with s and cosine with c so I can squeeze it in here. Sine squared plus cosine squared is 1. So we see that we have a constant speed of 5. And we're moving around a circle of radius 5. We're going counterclockwise. And the acceleration, when you have circular motion, is always going to point right back to the origin. Again, some sort of physics stuff going on. So notice that v dot a, if you were to take the dot product of these, you would get positive 25 sine cosine minus 25 sine cosine. So you get 0. And that implies that v and a are perpendicular to each other. They're orthogonal for all t. So it doesn't matter what value, it doesn't matter where you are on the circle, your velocity and acceleration will always be perpendicular to each other. And so we're dealing with a situation that is like this, where we have a circle of our motion. Our position vector is going to create a circle of radius 5. We're going to be going counterclockwise. Let's pick one location just to analyze. Let's pick t equals 0. That's simple enough. T equals 0. So when t equals 0, our position is 5, 0. If we plug in t equals 0, sine of 0 is 0, cosine of 0 is 1, so we get 5, 0. That's going to be our position at t equals 0. So at t equals 0, we're right there. So that's the vector r of 0. And then let's calculate the vector v of 0. So at that point, at t equals 0, we know where we are located on the curve. Now let's figure out what the direction of motion is. So the direction of motion, when we look at v of 0, sine of 0 is 0, cosine of 0 is 1, so we get 0, 5. So that is going to be our velocity vector pointing straight up. And that's a little crooked. A lot crooked. So this is a circle of radius 5. So that point right there is 5, 0. And that vector is supposed to be pointing straight up. That's the vector v of 0. And then we can take the acceleration, calculate it at 0, and what do we get? Plugging in 0 here, cosine of 0 is 1, sine of 0 is 0, so we get negative 5, 0. The acceleration vector is pointing straight back at the origin. It's going to be hard to draw, but it's right there. A of 5. So it's pointing straight back at the origin.
Why is it A of 5?
Oh, A of 0. Thank you.
Okay.
Yeah, it's 5 units long. It's 5 units long, but it's, yeah, we plugged in the 0 time value. So, yeah, sorry. A of 0. 5 units long. Pointing straight back at the origin. Yeah?
How do you, I can't remember how to determine which way you're going on the orientation.
So the velocity is always going to be pointing in the direction of travel. So you have two choices. When you have a parametrized curve, you could plug in a few points and see, oh, where are we with relative to the other points? You can see which direction are you going as you plug in t equals 0, t equals pi over 4, t equals pi over 2. Or the more sophisticated way is find the velocity vector and look at which way it's pointing. And that's going to indicate the orientation, as long as the curve is orientable. There are non-orientable curves out there.
I thought you said as long as the curve's oriental at first.
No, orientable. Yeah, we're not talking about oriental curves. I don't even know what that means. All right, relics. Oriental curve. All right, so this is a really complicated problem at first. It sounds very complicated. So this says, let R describe a path where the speed is constant. All right, the speed is constant. And then they just kind of say, oh, motion's on a sphere or a circle centered at the origin. And it's kind of like, is that really? Is that what that means? So they're implying here that R is a position vector that's tracing out a path, a trajectory, and it says where the speed is constant. And they're saying there, well, if the speed is constant, that means you're on a circle or you're on a sphere. And the obvious question is, why? Really? Is that necessarily true? Let's check. So, when we take a look at this, R dot R, so R, those are vectors, we can rewrite R dot R as the square of speed. Does everybody remember that? The length of R is the square root of the sum of the squares. But then if you do R dot R, you get the sum of the squares. Right? So if you do the sum of the squares and square it, then you're going to get those two being equal. So those two are equal. We learned the chain rule last week. Chain rule is when you have multiplication. Could be a dot product, could be a cross product, could be a function times a vector. We know how to do the chain or the product. We call it the product rule when it's multiplication. So product rule. So we can take the derivative of both sides here. Just like with real value functions, you can always take the derivative of both sides. No problem. The left side, we do first dot derivative second plus derivative first dot second. That's the derivative of the left side. What's the derivative of the right-hand side?
2 magnitude r. Don't you just bring it down like normal? No.
Not in this case.
It's a square.
What is the magnitude of r?
The squares.
Constant.
0.
0.
Oh.
Right? So the magnitude of r is constant. So magnitude of r squared is obviously constant. And if you take the derivative of a constant,
You get 0.
you get 0. So this assumption right up here, right there. So if we have a path with constant velocity, the path that's being described is a path where the following is true. Oh, I guess these we can add together. These are the same. We know that the dot product is commutative, so we can actually combine these two together. We can divide both sides by 0. Excuse me. Divide both sides by 2, getting 0 on the right. And this tells us that r is perpendicular to r prime at all t. And we just saw a minute ago that that's what happens on circles. R and V, if they're always perpendicular, that's forcing you in a circular path. In order to veer off that circular path, you're going to need a velocity vector that's not perpendicular to your position. It's got to pull you off the circle. So if you have a situation where we know that the velocity is constant, then we're going to be on a circle if we're in 2-dimensional space and on a sphere if we're in 3-dimensional space. So then that's how we prove it. So very, very, very tricky, very tricky. So the position vector and the velocity vector are orthogonal at all values of t. So geometric implication is what we just talked about. We're either on a circular path or on a path that's inside on a sphere, on the surface of the sphere. Seems dramatic. Okay, stuff we just did. Velocity vector, the speed is the magnitude of the velocity vector, and the acceleration is the derivative of the velocity. So, whoops, let's just do one more here. So this, actually, we graphed one that was very similar to this on GeoGebra just a minute ago. Let's graph this one just to see. So again, you have to use the word curve in GeoGebra to indicate that you're dealing with a parametric curve. What were those coefficients, 2, 3, and 4 or something?
3, 5.
Okay, so 3 sine t.
That's 23.
That's 23. That's too many. That's too many. And then the middle one was
5 cosine t.
5 cosine t. 4 sine t. Enter. Yeah, so we're going to get a tilted ellipse.
Getting cut off.
Is it cut off or is it not complete?
It's not, if we go 0 to 2 pi, we'll get the full ellipse. We actually went more than 0 to 2 pi, though, didn't we?
Yeah.
So we're actually doing 2 traces of the ellipse. If we go 0 to 2 pi, we'll get the full ellipse. Those dots are just indicating that you're looking through a plane to those points.
Alright, otherwise
What's on the bottom there, where there's just a gap?
Well, we should get. Well, maybe we won't get the full ellipse. Actually, I guess I've never analyzed it too carefully. I was thinking we would, but maybe we won't.
maybe it's rendered
Probably
differently.
should.
I feel like we
maybe
should.
This, maybe like the range of the cube that it's being rendered in isn't big
Yeah,
enough. I don't know
exactly.
if there's an
Oh,
adjustment
yeah.
for that.
It could be that our yeah, something like that.
You translate.
We're getting half of the ellipse when we go 0 to pi, so we definitely should get the full ellipse. So it's probably some sort of rendering issue. But we can sort of see what it looks like, at least partially. Okay, so we know at least geometrically we're dealing with an ellipse. And not that that's super important for the nature of this problem where we're just doing mechanics. The velocity here, let's just write this down quickly so we can keep going. We've got so much to cover today. So much math. I guess we're making up for Labor Day, doing some labor. All right, velocity. Any questions on this so far? Pretty straightforward. Just doing a bunch of derivatives. We gotta get to the harder stuff, don't we?
No.
No hurry? No hurry. All right, so that is how we'd find the velocity. It's how we'd find the acceleration. And let's see. Do they ask us for anything else? No. So we're just finding those. If we wanted to find the speed, speed's not going to simplify very nicely, though, because of the way this thing looks. We'll take the square root of the sum of the squares if we wanted to find the speed. But it doesn't look like we're good. Oh, no, actually, we are going to get simplification there, aren't we? Let's do it. Let's just check. Let's see if we get a nice simplified speed. Sometimes the speed unravels nicely. So we're going to get 9 cosine squared of t plus 25 sine squared of t plus 16 cosine squared of t. Yeah, so we do get constant speed. 9 cos squared plus 16 cos squared is 25 cos squared. So we have 25 cos squared plus 25 sine squared. Using the Pythagorean theorem, we get a constant speed. Constant speed. So what is this telling us then? We just saw something. If we have constant speed, it means that our path is on, or in 3 space, on a sphere. So we're on a sphere, and that ellipse is a path along. It's a path that's sitting inside that on that sphere. That's circular. That elliptic path is a subset of the sphere of radius 5. All right, let's keep trucking. Boing. Gravity is a force. And we are going to create a position function given the only force acting on the object is gravity. That's what we're going to assume. So we're going to build that nutty position function right there. The letters that they use are, I would say, not conventional, but they will work. So v of 0, that's conventional. That's our initial velocity. R of 0, that's our initial position. The thing that gets a little tedious when you're dealing with the symbols is that they have a v there and a v there. And so v sub 0 is the y component of the initial velocity. So you're going to just have to be a little bit careful there because that's kind of a little bit messy. Easy to get confused. All right, so the idea then, let's start with acceleration and then let's build. So we know that if we integrate, we are going to get velocity. So if we integrate, we are going to get, that's a constant vector. G is whatever, 16, 32, 9.8, whatever it is. Whatever planet you're on, whatever system of units you're using. So when you integrate a constant, you multiply by t, and then you have to add a constant of integration. So that's what we get for v. Now we have to figure out what c is equal to. Okay, let's plug in t equals 0. If we plug in t equals 0, that tells us that on the left-hand side we have v of 0, and then on the right-hand side, if I plug in a 0 for that t, that goes away. So then I get the constant vector is truly equal to whatever that initial velocity is. So that allows us to rebuild this and write it as v equals, we said the initial velocity is that u naught v naught vector. So we're going to get u naught, comma, minus gt plus v naught. So that will be our velocity vector. So we replace c with what it's equal to. It's equal to v of 0, which is the vector u naught v naught. So that's the initial velocity vector. And then we can build a little more. Integrate one more time. integrate. We can integrate term by term. We're going to get r. So this is going to be u naught t. Integrating a constant, we get u naught t. On the other one, we get minus 1/2. Sounding familiar? You've seen that 1/2 in front of the g before. V naught t. And then I'll put a constant out here. And then we do the same thing we did up there. We plug in t equals 0. So r of 0 is going to be, let's see, if we plug in 0 here, doesn't that all go away?
C.
So we get c. So this c is equal to whatever we're letting the r naught vector look like, and that's going to be x naught, y naught, according to what they decided above. So this tells us then that our position function building from gravity, we're going to have u naught t plus x sub 0, comma, negative 1/2 g t squared plus v naught t plus y sub 0. So that is our position vector, where we assume that we're starting at x naught, y naught with some initial velocity of v naught, comma, u naught, comma, v naught. So there's our position. So one more thing that we want to do here. Usually, we don't know what u naught and v naught are. We usually know what x naught and y naught are. We say, okay, position the origin. That's where you're going to launch your projectile from, or position it at 0, 5. Or those numbers are given. But when somebody says launch a projectile, what is the variable they usually give you, or what is the parameter they usually give you? Certainly they tell you how fast it's going to launch, like if you're shooting a missile or something, but what is the angle, right? When you're if you're shooting a basketball or you're launching a projectile, it's the angle that you're thinking about. You're not thinking about the component of the velocity in the x direction and the component of the velocity in the y direction. You're thinking about what's the angle and what's the initial speed. So we need to rewrite this because these guys here, those are typically unknown. And so what we can do very easily is come up with a representation for those two components by looking at the initial velocity vector. So we've got our projectile. We're going to imagine the initial velocity vector as being tangent to the curve. So that's going to be the initial velocity vector. So that's the vector. Again, this is confusing. That's the vector v sub 0. And the vector v sub 0 has components u sub 0, v sub 0. Oh, why did they do that to us? Okay, and then we have our launch angle, which is right here, and usually referred to as alpha or theta, depending on the book you're looking at. And you all know by now that if you form this triangle, you can decompose v naught into the horizontal component and the vertical component. So what we're going to do then is say this, which is going to be even more confusing because it has a v naught in it also. So the length of that vector is the speed. Speed of a vector, the magnitude of a vector is just denoted with absolute value bars. All right, so what we can do here is say that u naught, the constant, u naught, the component, is going to be the length of vector v naught multiplied by cosine of alpha. And the component v naught without the vector, the other v naught, that is going to be the length of the vector v naught times sine of alpha. All right, we're almost somewhere. Quite frequently, let's make one more assumption. Quite frequently, we assume that our initial position is the origin. So let's just throw that in there just to kind of clean it up a little bit. You can always move your axes around so that your launch is right from the origin. So let's look at our final form then, assuming that. So we have that our position vector is going to be u naught, which is absolute v naught cosine alpha multiplied by t plus x naught, which we just said, let's let that be 0. And then we're going to have minus 1/2 gt squared plus v naught, that's not the vector, so v naught the constant, so absolute v naught the vector times sine of alpha multiplied by t. So that will be our position, and y naught is 0. So this is an equation that you will see a lot of in here and in physics, where that absolute value of v naught is the initial speed, so that's a constant, and that alpha is your launch angle. And t, of course, is the parameter. So if you want the position at time 0, plug in 0. You want the position at time pi over 2, plug in pi over 2. So let's pause there. We'll take our 10-minute break, and then we'll do some exercises with the position function, with that cool position function. All right. All right, let's figure out this stuff. So dealing with a projectile, it's frequently important to know how far the projectile went. It's frequently important to know how high the projectile went. And it's frequently important to know how long it took to get from the beginning to the end of its path. All right, so let's analyze how we can do that. So we just talked about how we could assume the position that it starts at is the origin. And this is the initial velocity breakdown using alpha. So here's that triangle. We just talked about that. All right, so let's talk about first the time of flight. So the time of flight, let's figure out what the period is. How long does it take for it to complete its path? So if we think about our, let's see, I don't have, I guess I have it right down there. So this is what I pulled from the other page, except we said we're going to assume that the initial position is at the origin. So those are gone. What has to be true when the object lands? So the height is 0.
And also, pretty much the velocity is the same as when it started, except the y.
Yeah, if we
is
have
inverted.
symmetry, that's absolutely right. If we have symmetry, the velocity should match, right? So the piece that we typically will use to figure out what the period is looking at that y value and setting it to 0 to figure out what that time value is. So let's go ahead and do that. And here, we already did these two steps here. Let's just jump down to this, where we're going to write r equal to u naught, we're going to write as the absolute value of v naught, so the speed, the initial speed, times cosine of alpha multiplied by t. And then the second component is going to be minus 1/2 gt squared plus absolute value v naught, the vector, times sine of alpha multiplied by t. All right, so that's assuming that 0, 0, and that we've plugged in using alpha. Yeah?
So we're assuming that there's not going to be drag?
Yes. No drag. No drag in here.
No drags.
Just pure math.
And same thing for the homework, no drag?
No drag in homework.
Okay.
Coefficient of friction is 0.
Okay.
You're not living
It's
down
just
this
going to go
line.
right onto the paper. Coefficient of friction is 0. All right, so let's set that y value equal to 0 to figure out what the when the touchdown happens. So we set this equal to 0, and then we solve for t. So we'll get 1/2 gt squared on this side.
The y part.
And now, we typically don't do this in general practice, but here we know that t equals 0 is one of the t values that corresponds to the object being on the ground. That's the launch point. So we're just going to divide out that t. Right, we're going to just get rid of it. Normally we would pull everything to one side and factor, but we know what's going on at t equals 0. So we'll just assume that t is not 0 because we're looking for the end point. So we're going to divide out a t. We're going to divide by g, multiply by 2. Okay, so that is the time value for when the projectile lands. And then if we plug that into the x component, that will give us the range. Will you follow that? So this is going to tell us our period, which they usually use capital T to represent that. So that's the time that the object is in flight. And then if we want to know what the range of it is, we just plug that in as the t value into the x component. So we come over here, look at our x component right there. So let's go ahead and find range. So we're going to do, I think he uses a capital R for this. So it's just this x value right here with the t replaced with this.
Doesn't look like he really uses anything, just range equals.
Oh, has he just used the word range?
Yeah.
Okay.
Although in the one above, he used time of flight equals t equals.
I'll just use an R. That seems pretty clear. Everyone okay with that? Then we just combine like terms. We're going to have a length of v naught squared and then a 2 sine alpha cosine alpha, all divided by g. Which if you want, you can use a double angle identity, which he does in this book. Changes that into a sine of 2 alpha. So that would be our range.
Is range a vector or is it a scalar?
Scalar. So it's telling us the actual distance traveled, the lateral distance traveled, not the distance along the path, so the lateral distance. Right? We'll do arc length in the next section, which we'll use to figure out the length of the trajectory. But this is just the range, so the lateral distance. And so any logic questions there? Why we would do what we did? Set y to 0, when it hits ground, y is 0. Figure out that t value, plug it into x to get the range. Yep.
So are we just, like for the exam, are we just going to memorize like what our time of flight, our range, and our max height equations
You
are?
can memorize those, but most of the time you just sort of do it from scratch.
Okay.
You know, it's not that complicated to build it up. If you're given your alpha and you're given your v naught, this v naught, the initial speed, it's not too hard to just build. You can memorize those
So
for
just
sure.
try or memorize that specifically.
This you definitely want to know.
So
yeah.
specifically
Yeah.
memorize that, and then you can build up.
Yeah, then you can build up from there pretty easily. And even generating that, you should be able to do. I would practice that. It's a good exercise to be able to build up to this from 0, negative g. It's a really good skill. So the other one, the max height, we just take the period, divide it by 2 because we have symmetry, plug that into the y value. Right? Height is going to be measured by y, lateral distance by x. So if we take the period and divide it by 2, that's going to correspond to the t value where the object is at the high point. So we'll just take that, divide by 2, the 2 goes away, and we substitute that in, not for x, but for y. And that will give it to us. Give us the max height. So that's what they're indicating here. Period divided by 2 plugged into the y coordinate. And we'll get it. All right, let's do one. So I think I have 3 on here. We'll probably just do 2 of them because we need to get to the next section too. Start. So rock is thrown from the edge of a vertical cliff 40 meters above the ground at an angle of 45 degrees above the horizontal with a speed. Assume the origin is at the foot of the cliff, blah, blah, blah. So let's just sort of picture this. We're imagining the origin at the bottom of the cliff. So cliff is like that. And we're saying that this is at 40 meters high. And we're going to toss this rock off. And the angle is 45 degrees. So let's put 45 degrees in there.
45 up or down, above the.
Yeah, it's not going to matter though, right? They're both 45. Right?
I think it's.
Oh. I'm sorry. Thank you. Yeah, sorry. You are 100% right. Yeah, we're throwing it. We're not kicking it. Right, so we're throwing it. Thank you. So we're throwing it at an angle 45. So it's going to look more like that. Yeah, thanks. We're not kicking it. We're throwing it. So our launch angle 45 degrees. And the height is 40 meters. And the initial velocity is 10 root 2 meters per second. All right. So find the velocity and position vectors graph. So I just copied that thing over here so we didn't have to deal with rewriting it a million times. So it's right there. So let's go ahead. Our position is going to be 10 root 2 times cosine of the angle, which is root 2 over 2, multiplied by t, plus x sub 0, which is 0. We're just using the y value at 40, but the x value at 0. And then we're in meters, so gravity in meters should be 9.8. So that's going to be 4.9 times t squared. Plus, again, the absolute value of the initial velocity vector, which is called the speed. That's 10 root 2 sine root 2 over 2 times t, plus the initial position is 40. So a little bit of simplification here. And that should be a t squared over here, minus 4.9 t squared. 9t squared. All right, that is our position. So graph that. Yeah, we already graphed it up there. It's just a parabola. It's just an arc. Determine the time of flight and the range. So again, here I feel like it's just easy to, once you've got your position there, time of flight, let's figure out when it touches down. So let's ask ourselves, when is the y value 0? So let's go in here, set that equal to 0, minus 4.9 t squared plus 10t plus 40 equals 0. That thing does not look factorable, so what would we do? Quadratic formula or something to get your t values. But that's not going to be, that does not look factorable. And I'm not going to go through the details of solving a quadratic. You know how to do that. So you will solve that for t. Quadratic formula or a graphing calculator or whatever. And the last part here, or the second part of that one, the range of that object, what do we do once we find that t value to get the range? Plug it back in for the x coordinate. If you plug it into the x coordinate, you're going to get the lateral distance, which is what they call the range. So that's how far from the cliff the rock is landing. And then that final piece there, maximum height of the object. So this is a little different. 2 questions all at once, yeah.
Where did the over 2 go? Like the root over 2.
Root 2 times root 2 is 2, so those cancel.
Okay.
So, does that make sense?
Yeah.
Yep.
Yeah, where do we do B?
Where do we do B?
Yeah, graph. Oh, graph. Oh, okay.
There's my graph.
Okay.
There's my graph.
Oh, I needed that so bad. Thank you.
Right
E
there.
is going to be negative 10 plus or minus the square root of 884 over negative 9.8.
All right, I'm ready. Say it again.
Negative 10 plus or minus the square root of 884 all over negative 9.8.
And so obviously we're choosing the positive time value. The negative time value would be, back through the cliff into.
Actually, because it's a negative on the bottom, wouldn't you want it to keep a negative instead of...
Oh, that's a good point. We have to be careful there. What is the square root of that's going to be? Oh, yeah, you're right. We will have the negative. We are going to choose the negative because if we choose the positive, then the top will be positive, the bottom will be negative. That is a negative 9.8 down there?
Yeah.
Okay,
So,
yeah, so then.
the values
right.
are like negative 2.01. It's a non-rational number, and then the other one is 4.054.
An unrational number. I like that. Unrational. Yeah. Yeah, cool. So that's 4.05 seconds, and then you plug that in for the t value and the x coordinate, and you're going to get the range.
So just times 10?
Yeah. Times 10. Yeah, exactly. Great. Good observation. So the range is 10 times that, so 40.5 meters. Yeah, good. You realize it was that simple.
I know.
Once we have the time value, then it's simple. Yes, multiplying by 10, one of our favorite things to do. And then how about the, so here, let's use some ingenuity here. Because we don't have symmetry, we can't say, ooh, take the time value, cut it in half, and plug it in to get the max height. You have to be a little more clever here.
Derivative of the y component, set it equal to 0? Side chart?
So if we take a look up here, if we want to have the, right there at the top there where it crests, the y component of the velocity is 0, right? So if we look at the velocity vector, so we'll come in and take the derivative of this y component, set it to 0, get t, and that will be the t value that corresponds to the max height. And then we plug it back into the y coordinate. Yeah, good. Precisely. Okay, one more of these. Let me just think about this one versus this one. I want to do both of them. Let's just look at this one. Okay, so here, consider the motion of the following objects. Assume x-axis points east, y-axis points north. The positive z-axis is vertical and opposite of gravity. Ground is horizontal, and the gravitational force x on the object unless otherwise stated. And only gravity. Okay. All right, so we have a baseball. I should have grabbed that equation from the previous slide just so we have it to reference. Makes it a little bit easier.
You could just write it on the whiteboard.
Could do that also.
That wouldn't be technological enough.
Yeah. We need more technology. All right, so there's our equation. That's our equation. So let's take a look carefully here. So the ball is hit 3 feet above home plate. So 0 for x, 3 for y. Make sense? And then they give us the initial velocity vector. So we find the magnitude of it to get the magnitude of v naught. Right, that would, everyone follow that? So let's go ahead and find the magnitude of the velocity vector. So that's the square root of the sum of the squares. 900 plus 900 plus 6400. Whatever that's all equal to. So certainly 10 can come out. So that's going to be 18. Is that 84 minus 2? 82, I guess. I think that's right. Are there any perfect squares in 82? No.
10.
You agree with 10 root 82? So that'll be our speed. And let's go ahead and start substituting things in. So we're going to have our position vector is going to be the speed, 10 root 82. What is going to be alpha?
45.
So we are thinking about, if we think about the initial velocity vector, can we use a triangle to represent alpha? Can you see which triangle we should be using to represent alpha? So if the velocity is 30, 30, it's 45, but the angle we're really looking at is the angle of elevation. So the 30, 30 is telling us that we're going to bisect, bisect some quadrant. Bisect, what did it say, north and east, I think, or something? So we're bisecting this quadrant, so that's the 45 piece, but then it's up, right? Everyone follow? So we're bisecting that quadrant, but then we're going up. So the 30, 30 bisects this quadrant, 30, 30, but then it's 80 up. So what we would need to do is figure out this hypotenuse based on the 30 and the 30. So we're thinking about that being 30, we're thinking about this being 30. So the magnitude of this vector then is the square root of 1800. So was that like 10?
42.
What is it?
30 square root 2.
30 root 2. Thank you. Oh, right. I know that triangle. I know that triangle. I've seen that triangle before. Yes. Excellent observation. 45-degree triangle. And then now the triangle that we're looking at is a little different, correct? So now we're going to use that as the diagonal. And we're going to use, I didn't want to have that be a vector. We're just looking at it as a triangle now. And did we say the vertical piece was 80?
Yeah.
Yeah.
So probably not to scale here, but the vertical piece is 80 and the 30 root 2 is here.
Very not to scale.
And that's alpha. Everybody follow that?
Isn't 30 root 2 the base?
Yeah, why is the hypotenuse?
The 30 root 2. Oh, why did I put it on the hypotenuse? Thank you. That's the base. I agree. That is the base.
And then the hypotenuse, that would be at 10 root 82.
10 root 82 here. That's going to be, oh yeah, it should be. Yeah, right? Yeah, that should be 10 root 82. So now, okay, question, Haley?
Yeah, so where is your triangle in that top one? Is that not?
Well, it's coming out of the board.
It's like you're looking down at it.
Yeah, so this is the view from the positive z-axis looking down.
Oh, okay.
You know, so we look down and we don't see the actual, trajectory of the ball. It just looks like it's a line.
Okay.
So the ball is going that direction, but then it says it's going, but it has a vertical component of 80.
So it's 80 like that?
80 is the vertical part.
Yeah, so in your triangle,
Yeah.
that's 80.
Yes.
Okay.
That's 80 there. Right, that's 80.
That makes sense.
Yeah, that's 80. And then the initial velocity that we figured out when we did the sum of the squares, that's going to be that 10 root 82.
And then your block marker.
And the bottom one's got to be 30 root 2.
Okay.
So then we do tangent. Usually tangent is that one. And what do you get as an approximated angle in degrees? Since with trajectories, we usually use degrees. So that will be, somebody got it? 62. Thank you. 62 degrees. All right, we're flying now. So then we can plug this in here. Alpha is 62 degrees. So we have a couple of options here, actually. Now that we've built that triangle, we can actually put cosine of alpha and sine of alpha in right away because we actually completed the triangle. So cosine of alpha is adjacent over hypotenuse. So we could absolutely do this. 30 root 2 over 10 root 82 times t. X sub 0 we said was 0, comma, minus, we're dealing with 32 feet per second here, so we're going to get minus 16. And then The V naught is 10 square root of 82. Sine of alpha is that over that. Yeah, we're going to have some cancellation. That's super nice. Times t. And then the y0 was plus 3, I believe. So let's see if I can move that out of the way a little bit.
Professor?
Yeah, go for it.
Why the hypotenuse is smaller than the base?
Yeah, that's not a good
Yes,
thing.
we are.
Let's figure that out. So we came up with 30 root 2. And that, did we double check that answer there?
What's smaller than what?
So we factor out 118, 82, 10 root 82, square root
But
82. 10 root 82 is 91.
Yeah.
Yeah, no.
It's not smaller.
What?
So, but 10 root 82 is smaller than 30 root 2,
Yeah.
right?
Yeah, it's 14.
Do we see it?
I did the a squared plus b squared equals c squared.
No, it's not.
Works. So.
It does work?
Yeah.
It's not.
30 root 2 is around 42.
Yeah.
Oh, 30 root 2 is 42.
Yeah, but 10 root 2 is just 14 something.
This one right here is around 90. That's around 90.
That's 10 root 82.
Not root 2.
10 root 82.
Yeah, I think he said 10 root 2.
Yeah.
Yeah. So it's that matches up. And definitely you check the the sum of the squares better match. If the sum of the squares doesn't match, yikes. All right, so then we have a bunch of cancellation. And so our form for our position at any moment, 30 root 2t, comma, minus 16t squared plus 80t plus 3.
That's only really a two-dimensional vector.
Yeah. Right. There's no drag, there's no air resistance, there's no sideways wobble. That ball is straight in the plane.
It said it was spinning.
I thought it said it was spinning.
The ball is spinning, but not out of the plane. There's no whatever that's called.
Real quick, where did the negative 16t squared come from? I know I'm just like adding wrong.
Yeah, no problem. That's we're assuming feet per second, so we're assuming the
okay.
imperial system, so we're putting a 32 in there for
Okay, got it.
for G. So that's our position vector. Sketch the trajectory as just the ball in the air. Determine the time of flight and the range of the object. So
The acceleration is 5. It's now 16.
say that again.
The acceleration is 5.
Oh, we're not using. Oh, we're a ball. We're not gravity, right?
Yeah, but you use 16 over there.
Right. I know. That's what I'm saying. Yeah, when we're hitting a ball, we're not dropping it, right? So the acceleration is not due to gravity. The acceleration is due to our powerful slugging ability, not due to gravity. So we're not. So we need to. So this right here, this is acceleration due to gravity, but here our acceleration is due to.
So it's 5 over 2?
So we should be plugging a 5 in there for G. So that G in general is just acceleration.
Wait. That's horizontal. This is for horizontal. Yeah, you got
Oh, what am I thinking then?
Also, when does T start? When the ball.
Hold on, let me think. Hold on. Let me just think.
Everybody stop talking.
Hold on for a second. Wait, acceleration. After we hit the ball,
your y is right, your x is wrong.
Yes.
the y is right, the x is wrong.
No,
Oh,
you are not by yourself.
oh, you know what we did was we dragged in the equation. Oh, we should have just rewritten this equation because this equation is assuming that we start at 0 and negative g, right? So there's going to be the vertical acceleration due to gravity, so the negative g part is there. But this part here, the original vector, where do I write it? The original, that's the part. I pulled in that. Maybe that's why I didn't include it originally. So instead of 0, negative g, aren't we dealing with this? Right, that's our initial acceleration. So we're just going to have a modification in the x component.
You're
I
gonna
didn't think
multiply
about
everything
that.
by 5?
So let's see what happens. Let's just integrate real quick. So we're going to get 5t minus gt plus our initial velocity. And then, and what was the initial velocity here?
30, 38.
And okay, we're in 3 dimensions also. Back up a little bit. Hold on. Don't write this down yet. We're in 3 dimensions. We're in 3 dimensions.
Can I erase like the entire?
Hold on.
Should I just?
So what should the vector be for the
Rewrite.
acceleration then?
5, 0, t.
So what did you say?
Ignore that.
Let me read the question again. So the way we have it, x points east, y points north, the positive z is vertical and opposite of gravity. The ground is horizontal and the only gravitational and blah blah. So
It's gonna be 0.5.
so that what's it going to be?
0.5 g.
You think it's going to be 0.5 g?
Because x-axis points east.
Negative
So-
G.
Well, yeah, negative.
But
g,
this, but the ball is going 30, 30, 80. The ball is going into this quadrant. I got to think about this for a minute.
And up.
Yeah, it's going up, but the
Let's do this one.
But it says it produces horizontal acceleration of the ball in the northward direction.
right.
So it should be 5.
Zero. It should be 0.5 g.
I guess it's just
Can we just assume it's a foul
Based
ball
off
and
how-
doesn't count?
No, it would be
All right, let me
0.5.
think about this for a minute, guys. That's not clear in my head. The two competing options are this. So the ball is going this direction,
X is east.
and if we
Yeah,
say,
at the top. That's why I'm giving it.
He's right.
Yeah.
Listen to this guy.
okay, go ahead, Omar.
So since x is points east and y points north, and there's horizontal acceleration in the northward direction, it has to be 0.5 negative g or g or however you want to put g in there.
Oh, right there.
Yes, sir.
I didn't read that word. Yeah. Yeah. Okay. Totally agree. Yeah. Totally agree. So if we're going to use the fact that the acceleration is, I was thinking that it was bisecting the quadrant north and east. I thought it just said it has an acceleration of 5 feet per second squared, but it says 5 in the northward direction. That's the spin on the ball that you were talking about.
Yeah, he's going towards the short side of the field.
Got it.
Game are we playing?
The short side. Okay, so our acceleration vector then is,
0.5 negative b.
0.5.
everybody agree?
Okay.
All right. So this is east, north, and up. East, north, and up. Sorry about that. I got tangled up on that one. All right, so our velocity vector is going to be, when we integrate this, we're going to have our constants. We're going to have this, 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 and then our constant vector that we add. Didn't they tell us
30,
30,
30, 80.
30, 80?
10 root.
Right, that was the initial velocity vector that was given. So when we integrate and we set time to be 0, the constant is the initial velocity vector. So then we combine these guys, we get 30, 5t plus 30 minus gt plus 80. And then we're going to integrate again, and we get 30t 5 halves t squared plus 30t comma negative. Here we get gt squared over 2 plus 80t. And then what's our initial, what was it, 3 comma?
0.30.
0.30.
Yeah.
0.30. And then we combine those, plug in our 32. So we're going to have 30 times t, comma, we have to come up with, just add a 3 in. Plus 30t plus 3. And then plug in the 32 here, so we get minus 16t squared plus 80t. All right, there we go.
Wait, shouldn't it be 0, 0, 3?
Yes, it should be because its upward direction is.
Yes, agree. Does everyone know why it's 003? Yeah, it's above home plate,
Which we took as Y.
which we took as z.
Well, yeah.
Z is up.
Yeah.
Z is up. So 0.
After we fixed everything.
Yeah, after
Z
we.
is up.
Yeah, now Z is up. Plus 3. Whew. All right, there we go.
That was a
Yeah, that was
experience.
more than I bargained for.
Mm-hmm.
Okay, so there's our position vector, and then if we want to know what we are curious about when it hits the ground, Z is going to be 0. Solve that for t. That'll give us the time of flight. So we're going to set Z equal to 0. So minus 16t squared plus 80t plus 3 equals 0. And Grant, you have your fancy
Oh, you want me to do that?
calculating ability. So that'll be our t value. And then while you're doing that, let me just read what else we want to find. Time of flight, range of the object, max height. Okay. So let's put a big X through that. Let's not look at that one. We'll look at this one. What'd you get for t, Grant?
Doing it now.
So then what are we going to do with that t value to get the...
Negative 80 plus or minus the square root of 6,592 all over negative 32.
Oh my goodness.
And that was 600 what?
6,592.
Thank you. And again, we're going to choose the negative because the positive is going to give us a negative number. So we're going to choose the positive. And what's that approximately equal to if you...
5.037
seconds.
So plug that back into.
So plug that back into what? So if we want to figure out, again, we don't have symmetry, so we're going to have to take a derivative to figure out the max height. But if we want to get the range, where are we going to plug that into? So if we plug that in here, multiply those two together. What about the max height then? Which derivative do we have to find? Y prime.
Yeah.
Set it equal to 0, get a t value, plug it back into Z to get the max height. Yeah. Whew. All right, let's stop that. Let's go. Let's get away from that problem. That was hard.
That was hard.
That problem was so hard.
Oh no. Oh no.
Arc length.
Yay! Paper. Forgot even what the point of that problem was.
The point of the problem
I know.
was baseball's so complicated.
Yeah. Is that what we were looking for, the time? Or is that
Yes. So how long? The time of flight, the max height. Yeah.
So there's the actual calculus involved with finding initial velocity, how far the ball goes, and the height, and the stuff that they do for the home run derby.
Yeah, that sounds kind of fun actually.
That cast is more complicated than it sounds.
Yeah, right.
Home run derby is during the All-Star game, right near the All-Star game. They figure out who can hit the most home runs. Oh. And, you know, how far they hit them. And, all right.
How fast they hit 'em.
How fast they hit them. Okay, Calculus 2. In Calculus 2, you found arc length using the arc length formula, where you had, this should look familiar, where you take the square root of 1 plus y prime squared, and then you integrated it. So that was your arc length formula. Well, we're going to do it a little bit differently here because we have our curves parametrized. Our curves aren't given to us as functions. They're given to us as parametric curves. And the idea is super similar. If we go back, when you originally did arc length, you came up with this formula from the Pythagorean theorem that said this. And you'd use some algebra to do it. I'll show you how we're going to do it differently. But that's what you did in Calc 2 to get the arc length differential. So when you're dealing with arc length, you are dealing with the combination of differentials and increments. Increments are always exact measurements. They're exact differences. An increment is not an approximation. An increment is an exact distance. And so what we do is we set the differential and the increment equal for the x and the y. The x's and y's are thought of as independent variables. And with independent variables, you always set them equal to their increments. And it's the dependent variable that's approximately equal. The differential is approximately equal to the increment. So in Calc 1, you did it with, you wrote this equation down. You wrote dy is equal to f prime of x dx. I can't even write it on this board. But, so you did it in Calc 1 where you said delta y is approximately equal to dy. So dy was f prime of x dx, and that was approximately equal to delta y. So we do the same type of thing here. This is a piece of arc. We want to know the distance from here to here. Our functions are given to us as functions of t, so we have to somehow convert. That's what you did in Calc 2. You said, hey, let's convert it to a dx so that we can then add up all these little bits of arc. Here, let's not integrate quite yet. Here we look at this differential triangle, and we do a similar type of thing. We see that ds squared is dx squared plus dy squared. And we solve for ds. We choose the positive square root, and we get that. Now what we want to do is somehow get a dt on the outside so that we can integrate with respect to t. So what we do is clever math. We multiply by 1. So we multiply each one of these by dt squared over dt squared. And if we do that, we can factor 1 dt squared out. So everyone agree all we do is multiply by 1 twice? No big deal. So the numerator dt squared, that comes all the way out as the dt. And then we're left with dx dt squared plus dy dt squared. And that is our arc length formula. So this is ds. S is representing arc length. If we integrate both sides, we will get arc length equals the integral of this. So we've now taken and we've turned a sum of a bunch of little pieces of arc into a total arc by integrating. So this is how we would find a little piece of arc. A little piece of arc is approximately equal to that diagonal right there. And so we do the Riemann sum thing, and we let that little piece of arc shrink and add them all up, let n go to infinity. The integral of that will give us exactly the arc length. So that's the arc length for a parametrized curve. So let's try it. It's not as bad as arc length in Calc 2, trust me. Because you remember, I'm sure you remember how bad that was.
I remember.
So here, dx dt is 3, dy dt is equal to 4, dz dt is equal to 1. You also could just write the velocity vector down, totally fine. Do that. To figure out your 3, 4, and 2. So this curve is in 3-dimensional space, so we're going to have one extra piece. Sometimes we use an S, sometimes we use an L. Doesn't matter what you want to use for arc length. 0 to 1, square root, sum of the squares of the components. So we get 9 plus 16 plus 1 times dt. So that's going to be square root of 26. T, 0 to 1, we get root 26. So that is
That's
our...
it?
Yeah. They will get a little harder. Everything seems so easy after the baseball problem. Yeah, we'll get a little harder. But it also conceptually makes sense. If you integrate speed, you get distance. Integrate speed, you get distance. If you integrate speed, you get distance. All right, so let's try one that's a little harder. So here, let's go ahead and figure out, let's write it this way as velocity, since we kind of now see that that's really what we're dealing with. And the magnitude of the velocity vector is the speed. So that's going to be 16 sine squared plus 16 cosine squared plus 9. That's all going to be equal to 5. Okay, so now we're going to integrate a speed of 5 on the interval from 0 to 6 pi. So we get 30 pi for that one.
that like cruising speed for you?
It's much better.
That wasn't even that bad.
No, it's not.
How did you get the 5?
So 16 sine squared plus 16 cosine squared is 16. Right? Sine squared plus cosine squared is 1.
16 plus 9.
So 16 sine squared plus cosine squared is 16. So sine squared plus cosine squared is 1.
Sorry.
Okay, I think that's the end of that slide. Yes, that's the end of that slide. Any other questions on that? So a lot easier than those Calc 2 arc length problems, because here we're doing it parametrically and it just breaks it apart into something that's a lot less difficult to integrate.
Like Pythagorean theorem. Kind of like how I use Pythagorean theorem.
Yeah,
That's something we know.
that's something we know. Simple. Dx squared plus dy squared is ds squared. Okay, so let's up the ante a little bit.
Wait.
So what about if we have a polar curve? Not too bad. Polar curve. So with a polar curve, we're writing the radius as a function of theta. So r equals f of theta. We get that. And when we are taking a look at polar curves, we use these two equations. X is our cosine theta, y is our sine theta. And what's going to happen, I don't want to go through all the details just because we don't have a lot of time today for some reason. And baseball is so slow.
Yeah, it's the
Baseball is so slow.
No wonder
That's
they're
the
trying to
whole
speed up the
problem.
game.
What's that?
No wonder they're
I
trying to speed
know,
up the
honestly.
game.
Yeah, exactly. They want to speed up the game. There should only be 2 strikes and you're out. So this will be the formula that we're going to use if we're going to use polar. So it's not complicated, but if you take this r value right here and you substitute it into our polar equations, and then do what we just did with dx d theta and dy d theta, except we used t on the previous slide, it turns out that these formulas are identical. So you have 2 choices. If you have a polar curve, you could go back to the parametric representation, or you could use this shorter cut if you won't want to remember it. In general, my recommendation is not to remember an extra formula. If you already have a formula that you kind of know, and you just have to extend it a little bit, that's usually a better way to go. This one's not that complicated to remember, though. Instead of dx and dy, you have f and f prime. It's kind of up to you. So we can do it. We'll see what happens. Let's see. Did I have one down at the bottom? No. All right, so let's take a look at this cardioid. So some of the graphs that you should be familiar with are circles, lines, and cardioids. Are you familiar with cardioids? Oh, yes, I'm familiar with cardioids.
Please, no more cardioids.
Yes. The cardioid, it has other names that are more colloquial, but we'll call it a cardioid. Obscene? Is that the other word?
Okay.
Yeah, if you were in Calc 2 last semester in this classroom, there was some crazy talk about the cardioid that I will not repeat.
Thank you.
Yeah. So let's talk about, if you haven't graphed a cardioid in a while, let's just sort of think about it. We think about a radial line emanating from the origin going to the right first, and we're just rotating counterclockwise. And we want to plot the r values based on the theta values. So when theta is 0, we're pointing this direction in the positive x-axis. We plug theta equals 0 into our equation. Sine of 0 is 0. 2 minus 0 is 2. So the r value is 2. So that tells us in the direction, positive x-axis, we're going to go 2 units from the origin and plot that point. Okay, and then we rotate. Usually we can just do this by 90 degrees, pi over 2. Plug in pi over 2. Sine of pi over 2 is 1. 2 minus 2 is 0. So we're plotting the dimple right there. rotate over to pi. Sine of pi is 0. 2 minus 0 is 2. So make sure this is the first point that may not seem like it's plotted properly. So if you go to pi radians and you end up with a r value of +2, you go in the pi direction 2 units. So pi over pi comma 2 means go to pi and then out 2. Right? And then 3 pi over 2. Sine of 3 pi over 2 is -1. You get a 4 there. So that says go to 3 pi over 2 and go 4 units away from the origin. And then it plots that. And 2 pi puts you back at 2. All right, so the curves that we tend to see frequently, lines, circles, and cardioids. Cardioids always have the equation where those two are equal in magnitude. It could be 2 and -2. It could be 2 and +2, 5 and -5, 5 and +5. That can be sine or cosine. So if you plot a few of these, that's what a cardioid looks like. If you kind of know that it's a cardioid, then doing this rotation where you separate by pi over 2 at a time allows you to graph it pretty quickly. All right, but they want us to figure out what the arc length of this cardioid is. So we have the formula that they use is that arc length is going to be the integral of the square root of a bunch of stuff. Square root of, they wrote it as f squared plus f prime squared d theta. And then we're going from 0 to 2 pi to get the entire thing. So that'll be the formula that we use. We could change it to a parametric thing, but this formula is not too crazy. So let's go ahead and do this. So we're going to integrate from 0 to 2 pi, square root. F squared, that's what this is represented by here. That's f. So we're going to square that. So we have to FOIL it out. We get 4 minus 8, blah, blah, blah. So 4 minus 8 sine theta plus 4 sine squared of theta plus the derivative squared. So off on the side, let's make sure that we note what the derivative is. Looks like it's going to be minus 2 cosine theta. So then we plug that in. Squared theta. So we're just taking the r value, taking its derivative, squaring them both, adding them up. And 0 to 2 pi. Now, we'll talk a little bit about integrating through the cusp there. So that's, what's that going to be, 4? This is going to be 8 minus 8 sine theta. So one thing that can happen, you've got to be a little careful when you're finding arc length, because right here, we've got this cusp here, and typically you don't like integrating through cusps. Often that can cause a problem. That can be a place where the function's not defined. It can cause an integral that doesn't exist. So one option, instead of integrating right through that cusp there, you could integrate from minus pi over 2 to pi over 2 and then double it. Would totally work. Right? That way you could avoid the cusp. Now typically with cardioids, if they're centered at the origin like this, I typically it's not going to matter. You can just integrate 0 to 2 pi and it works, typically. If you want to be safe, if you come up with a funny answer, then that's something to check. If you come up with an answer that doesn't make sense, check. Integrate to the cusp and then double it. Use symmetry. Don't do anything crazy if you come up with a funny answer. Okay, so now we have to integrate that. How do we integrate that? Anyone remember how to integrate that?
Set x equal to 8, something like this. You substitute it in with x.
U sub's not going to work in this particular case.
Is there an identity for that?
That still won't work. What's that, Grant?
I said, is there an identity for that?
Well, if we're going to integrate it, it's going to be with an identity. And so let's make sure when we look up here, sometimes in the book it has a T up there to indicate that you're supposed to use technology. It doesn't say that here, but if you get to something that you're not sure whether you can integrate or not, you definitely make sure that it's not expecting you to use a calculator or something. So it's not asking us that, so then we definitely need an identity. So identities. What identity? Anyone notice an identity that we might be able to use?
It's pretty close to 1 minus, like x squared. Like it's the square root of 1 minus the thing squared.
Is this the
I don't
8
know what
secant
the
squared?
word is.
Which one?
Secant? X?
No. It's going to be like it's going to be a half angle identity modified or something like that. So let's take a look at the identities that we know off the top of our head. So we know that something like sine squared of theta, we can reduce that to 1/2 minus 1/2 cosine, minus 1/2 cosine 2 theta. Cosine 2 theta. That's an identity that we can use.
But and cosine
Yeah,
is
it's
cosine
better
squared
out
just the
of it.
opposite of that?
And cosine squared looks a lot like that. That's
Is
not,
it plus?
Cosine squared.
No.
except it's plus.
It is plus.
Yep,
Oh,
that's
I-
plus.
So
That's not looking very promising though, is it?
Oh,
The 2 theta is the issue.
Also, don't you just put sine theta, not sine squared? Well, he's trying to go backwards.
Say that again about the sine. There's no sine squared here, unfortunately.
Right. That's the identity of rows.
Can't you just go straight from the sine squared over, and instead of it being cosine of 2 theta, it just becomes cosine of theta because you have a theta over 2? Like you can just set theta to be a different variable.
Yeah, you could do that.
Yeah. So.
But then we're still kind of tangled up though with the sine though, right? We still have this square root. If we square root that, we have a cosine over there and not a sine here. So I'm not sure which identity we should use. Somebody know which identity we should use? You don't know? We did this in Calc 2. We all did it in Calc 2.
In the My Math lab last year, if you had 8 minus 8 sine of something, you have to do like a substitution, like x equals like secant, like 8 secant to theta or something squared. You have to do something like that.
Really?
I don't remember exactly what it is for sine.
Let me think.
Sine, cosine, and all of them had like some
I know.
other trig
I
function
feel
you're
like we've had so
supposed to
many
substitute.
Yeah.
Based off the Pythagorean theorem. It's something squared.
Wouldn't that have? Yeah, that'd have to be a sine squared though, because then you set it to be.
If we had that, if there was a
Cosine
square, it'd be
squared.
totally
Oh,
different.
Yeah. If it was
I think
squared, we
there was
could
an
just use
example in the end of Calc 2 in the
Mhm.
note, like these notes.
Yep.
There was an example that's solved like at this point. We had some-
Do you remember what the identity is?
But I don't know how quick it is for you to pull out.
Yeah, it might not be too. We could pull it up. Let me think about it for 1 second, because the identities that we typically use are those which are called power reduction. We can use our double angle identities, but this is not looking like any sort of double angle identity. It's one of those ones that's got a weird trick. Oh, I bet I know what we do.
It has a weird trick.
I bet we multiply by a conjugate.
Oh.
I bet we
it,
multiply
that's
by
it.
a conjugate. This has got a weird trick. I think we do this. If we factor out that 8, let's factor the 8 out and just put it out in front and get it out of the way. So let's just pull that square root of 8 out and just clean this up by using, just put some 1s in there. So I have a feeling this might do it. I think that's what's going to do it. So let's see where we go with that. You may not want to write it down quite yet. I had Okay, so then in the numerator, we are left with the square root of, yeah, this will work. This will work. Because this is going to be the square root of 1 minus sine squared. And what is 1 minus sine squared equal to? Cosine squared. Square root of cosine squared is cosine. So we get this over this. Yeah, that would do Now we can use substitution. Does everybody follow that? So square root of 1 minus sine squared, that's square root of cosine squared. Square root of cosine squared is cosine. And now we can use u sub. So if we let u equal 1 plus sine of theta, du is going to be cosine theta d theta. Integration. Square root of 8. So now we're converting the variable. Let's just leave the limits unknown for a second. So it's going to be u to the minus 1/2 du. We'll come back to the limits in a second. So we're going to get square root of 8. U to the positive 1/2 divided by positive 1/2 means multiply by 2. U to the 1/2, that's 1 plus sine of theta to the 1/2. And then that's from 0 to 2 pi. Sine of 2 pi is 0. Sine of 0 is 0. The square root of 1 is 1. So this is all going to be 2 times the square root of 8, which we can simplify a little while ago. So that's going to be 4 square root of 2. All right. That will be our...
Wow.
So that'll be the arc length of our cardioid. Yeah?
I looked it up. The reason we didn't know it is because it's a hyperbolic trig identity.
Oh, yeah. That's a good reason not to know it.
Yeah.
Which hyperbolic trig identity is it?
It had like 2x minus pi over 4 over x, and it didn't say which one it was. But
Alright.
it said rewrite using hyperbolic identities.
Okay, yeah. Which we won't be doing. We'll do it this way. All right, let's stop there. You got what?
That's 16 pi on calculus. I wonder if I input something in this.
Calc 2, yeah, trying to remember all those integrals.
And I got cookie on my homework.